So this is second derivative test, which we've covered already, and also optimization. All right. So I want to give you guys some practice problems. They're all different applications of the second derivative test. Now, when you guys are looking at what we're doing here, okay, you know, if I just kind of flash through the reading with you, there are just tons of examples. In some ways, this is the longest section I've seen yet in the book in terms of number of examples they give you. It starts on page 343, okay? And they kind of go through a basic test example like we did in class. And they talk about how you might have, you know, an absolute minimum but no absolute maximum, an absolute maximum but no absolute minimum. Or you could have a relative maximum and a relative minimum. So there's all these different, you know, mathematical ideas. But then they start getting into examples. Maximizing volume. Maximizing a harvest. I think I'm going to start with this one, actually. Minimizing or maximizing a sustainable harvest. Inventory costs. It's a lot of examples. And I've just known from experience that it helps to see some samples worked out in class in addition to your own reading. But I'm pointing you there because you're going to want to kind of follow the models that are there. Okay? So, as far as you know, us starting out today, I'd like to start over here on page 358. I guess it's actually and 359. So maybe we'll try 56 here. Okay. Maximizing yield. They're talking about Waltz Walnut Grove. Okay. So, you know, this could be a farming problem, right? But the example in the book, I think they do a different kind of fruit tree, and then there's apples and oranges, and this could be any crop you want, okay? But we're trying to maximize yield. And so they give me a few facts. The total annual yield and tree density. They've determined that their walnut tree yield is fairly constant, right? It says 50 pounds per tree. So if you know that you're going to get 50 pounds of walnuts from each tree, and you want more yield, what do? Plant more trees. But you can't overdo it. And that's the point they're trying to make. This works when the number of trees per acre is 30 or fewer. They also find that because of overcrowding, for each additional tree over 30 in the acre, the yield decreases. I remember as a kid, my mom always did a garden outside. And we're not farmers. I mean, we lived in suburbia, okay? But we always wanted Mom to plant a watermelon. Come on, Mom, can't you give us... We couldn't ever grow a watermelon that would be bigger than an orange. Why? We didn't have enough resources. We didn't have good soil. We didn't have enough space in the yard. You know? You need space. You need resources. And so what they're saying here, okay, in that acre, yeah, you can plant more than 30 in an acre. You can plant more than 30 trees, 30 walnut trees. But you're going to take a hit a little bit. The trees won't be as fruitful, literally, right, as they would. So here's the question. How many trees need to be planted per acre to maximize the annual yield? Right? So you've seen the problem. And what I want to give you here is kind of an approach. How do you tackle a problem in optimization. Optimization. That's the question there. I always begin with the following. I always begin with the question, what am I trying to optimize? Well, what are we trying to optimize here? It said, look at the question. We're trying to maximize what here? Annual yield, right? So, we are trying to maximize annual yield. Okay? Now, then you have to figure out, do I know what the yield is? Well, they give me some information here. They say that the yield is 50 pounds per tree, maybe, or it might decrease. It might decrease, right? So you might wonder, well, how do you handle that kind of a situation? And this is where the examples can really come in handy, okay? Because people have done this before, all right? So let me show you. If you go back to they started on page 350. Well, really the next one. It's before that. So on page 349, they're talking about, well, how do you do this? The total yield for an acre. Figure out how many trees you have. Kind of like we did up there, right? Times the yield per tree. Kind of like revenue, guys, right? The number you sell times the price. I mean, there's a lot of parallels here with revenue. And now, in their example, they made a chart. And they said, okay, suppose you have 10, 20, 40, 50 trees. And then they started kind of changing what was happening here. Because in their problem, once they got more than 50 per acre, the yield started decreasing. Right? So we could kind of talk about this. And their suggestion was, if we want to write so let's do this. Whatever you're trying to optimize, this annual yield, let me call it AY of X. And I want to write a function representing annual yield. If I can write a function representing annual yield, this is my plan. I'm going to write a function representing annual yield. Then do calculus to maximize AY of X. That's my plan. So this is where their table, this is what they do. They say, hey, think about the number of trees per acre that you have. And if we multiply that by the yield per tree, then we'll get the total yield. But what I'd like to do is write a function. So looking back at the problem, first thing they tell me is the walnut tree yield is fairly constant at 50 pounds per tree when the number of trees per acre is 30 or fewer. Okay? So, you might have 10 trees per acre, 20 trees per acre, or 30 trees per acre, and in each case, we're at 50 what? Pounds. Per tree. So if you multiply by 10 trees, the trees cancel, and you get, hey, if you have 10 trees per acre, you're going to get 500 pounds per acre. Of course, if you have 20 trees per acre, then how much are we going to get from each acre? Well, we'll get 1,000 pounds. 30 trees per acre, 1,500. But you go any higher than 30 trees per acre, now the yield per tree is going to diminish. That's what they said, right? So that second sentence there, they find that because of overcrowding, for each additional tree over 30, the annual yield decreases by 1.25 pounds. So let me make this 31. If I go above 30, it's not 50 anymore. It's 50 minus 1.25. And you could multiply, and you'd get 31 times 50 minus 1.25. If I did 32, you would get 50 minus 2 times 1.25. And you could multiply. 32 times 50 minus 2 times 1.25. All right? See, I think that the hardest part here is coming up with the actual function for annual yield. You need a function that'll give me this total yield. Maybe I'll even call it Ty of x. That's what the book does. They call it Ty of x. May as well. I like their notation. Okay. So we know how to get the total yield in this situation. And what we don't know, I guess, is what happens if you have X trees. Because we don't know how many trees per acre is the right amount. It's definitely not 10 or 20. Right? I guess it could be 30, but is 31 better? We didn't actually work that out. Here, let me do that real quick. We got a calculator for a reason. Let me type in 31 times, well, 50 minus 1.25. Enter. Oh yeah, that's better than 1,500, right? So even though you're losing the number per tree, you haven't lost enough yet that it's a problem. But if we want to maximize our yield, we'd like to know how many trees per acre do I need? So if you make the number of trees per acre equal to X, okay, then how do we do the yield per tree? I'm going to pause and let you guys talk to each other about that, because that's probably the hardest part of the problem. And it's worth a little time and a little thought. Let me say this. When we go to write our function, okay, I think what we are agreeing upon, if I'm hearing you guys right, is that, you know, when you have a function, you also have a domain. And so based on my work below, my domain should be 30 to something, right? I mean, how many trees could you put in an acre reasonably? I don't know, 100? I don't even know if you could do that. But my X values, I'm not going to go less than 30, because at that point, well, this is what Stephen was saying, that I'm really kind of on another part of the function, and then like Brian said, well, then we know the answer is 30. Right? But I still don't have the function yet. The way the book does it is they let X be the number of trees per acre. Now I'm going to show you guys what Lauren was thinking, okay? And the interesting thing is that's what I was thinking too, all right? Instead of X, I'm going to use, so I'm going to kind of show an alternate approach down here. It's funny, I haven't even shown this approach completely yet. But I want to show the alternate approach because in my mind this made sense also. What if we let T be the number of trees over 30? Right? Because you have 30, 31, 32, right? I mean, that's the chart that I have above. And so instead of putting X, if you decide you want to do it this way, then you're going to put 30 plus T as the number of trees per acre. And the reason Lauren said she liked that is because then it's easy to talk about the yield per tree. The yield per tree we knew was 50, and then it was 50 minus 1.25, and then it was 50 minus 2 times 1.25. See, that's T. T is 2. And so in general, the yield would be 50 minus 1.25 T. Okay, see that? So, if we do it this way, then my total yield function will be a function not of X anymore, but of T. And maybe I shouldn't have used capital T because it's right there. But hopefully you could follow this. The total yield would be 30 plus T times 50 minus 1.25 T. That's the function that I need to optimize if I want to get the total yield. Of course, to optimize it, you're going to want to take first derivative. Maybe you'll do second derivative. What rule are you going to need to use here? Product rule, for sure. Right? Although I guess you could also simplify that. You could just multiply it out. For this problem, that might even be easier. Just multiply it out. And you don't need the product rule. All right. But I want to go back to the way the book does it so we can compare. So they throw X as the number of trees per acre. And now the question is, what about the yield per tree? Well, it's always 50 minus something. Right? And what we have to do here is we need to multiply something times 1.25. Now the question is, what's the something? What goes here? Do you guys know? Like for 31, that number is 1. For 32, that number is 2. So what are we always doing?
Is it x plus 1?
Why?
I mean, you're always adding 1 when you go up.
We're always adding 1 when we go up 1, right? See, we need that when we put x in, we get this number. And so, when x is 31, this number is 1. When x is 32, this number is 2. I didn't write it, but if x was 33, what would this number be right here? 3. How do you get it? Whatever x is, you got to subtract 30. Right? You told me if this is 33, that number is 3. So you take x minus 30 times 1.25. I don't think that's simple to come up with. But does it make sense now that you've seen it? Okay. If I give you that, then what's my total yield function going to be? Well, that's what goes here, right? Total yield of x would be, well, x times big ugly mess, this thing. So I guess that's 50 minus x minus 30 in parentheses times 1.25. All right. 2 different ways of doing the same problem. Let me get that on the screen so you can see it. So now we have a choice, right? The way the book did it, they have this function we have to optimize. The way we did it, we have this function we have to optimize. Now, I mentioned to you guys, if it were me, I would simplify here. So I would write down x times, and so this stuff here, let's see, it would be 50 minus 1.25x, and then it would be plus, what's 30 times 1.25? Let me work that out. Got a calculator, may as well. 30 times 1.25. Enter. 37.5. So I get x times, this would be 87.5 minus 1.25x. And so I would get ty of x is equal to 87.5x minus 1.25x squared. Now that's a problem that I know I can optimize. Matter of fact, what shape is the total yield function? Opening which way? So could you find the maximum? Of course you could, right? And maybe one last thing to share is just to go back here where Lauren's talking about this, doing it this way. If you did it this way, I would also think about simplifying. So 30 times 50 is 1,500. So this is ty of, I'll use lowercase t just because it's probably nicer. So I get 1,500, and then I get, we did 1.25 times 30 is 37.5. So then minus 37.5 t plus 50 t, and then minus 1.25 t squared. And so you get almost the same thing. Not quite though. 1,500 minus or plus 12.5 t minus 1.25 t squared. You go to optimize this, it's also a parabola opening downward, but it's a different parabola. You'll get a different value for t. But you'll actually still get the same answer in the long run in terms of what the total yield would be. So I guess I could show you that. Let me ask this. Should I finish the problem, then take break? All right, let's do that. Let's finish the problem and then take break. I'd like to show the two different ways of doing it because we started with that. So let me go ahead and kind of write it up at the top, and I'll show you the two different ways of handling this. Okay. So one way, we got up to here. We said ty of x is 87.5x minus 1.25x squared. The other way to handle it was ty of t is 1500 plus 12.5t and then minus 1.25t squared. So I'm going to do both of these for you. And we'll see which we like better. Okay, so doing it the first way. We need the derivative. Ty prime of x is 87.5 minus 2.5x. So what do you do now? You got the derivative. Well, hey, just for kicks, what's the second derivative? Thank you. What does that tell me? It tells me we're always concave what? Okay. If we're concave down, I know I'm going to get a maximum if I just find the critical value, right? So let's find the critical value. How do you find the critical value? Well, you set this 87.5 minus 2.5x equal to what? 0. So 2.5x is 87.5. Divide by 2.5. Do you get 43? Better do that. Work that out. 87.5 divided by 2.5. 35. Okay. Glad we used a calculator. So we got x is 35. So what does that tell me? 35 trees per acre is ideal. It will maximize what? The total annual yield. What about the blue way? What if you came up with this? If you came up with this, you would have said ty prime of t is 12.5 minus 2.5t. And then you say, well, set that equal to 0, right? So 0 equals 12.5 minus 2.5t. 2.5t is 12.5, and if you solve, you get t equals 5. But doesn't that make sense? Because what was t? Remember, t, this is the number of trees more than what? Than 30. So you get the same answer. I think that's cool. You get the same answer no matter which way you do it, as long as you're doing things correctly. And then, it doesn't ask this, but it could have. They could have said, well, what would the maximum annual yield be? right? They could ask that. Remember our table? If you go back to our table, we said, well, 1,500, but then it might be 1,511, right? So if you want to get the total yield, what you could do is go back to this original function and plug in, 35 for x, right? So let me see. Up here, let me just do second entry a couple times. Because up there I did 31, and it worked out fine. There it was. 31 times 50 minus 1.25. So what if I did 35 times 50 minus, and then if I insert a 5 here, well, look at that. That would be the annual yield, 1531.25. That's greater than 1,500. So yeah, 35 trees per acre would be ideal. So let's see. Moving through the examples. That example 5 kind of gives you an idea of how to do this harvest, this total yield. Next, example 6 from the book. I think I'll do if we have time. Or I might just turn you loose on one of them. We'll see. Because I think, honestly, having seen the one I just did, you could probably read the book and follow this one. It's all about deer hunting. It says Sussex County allows hunters to shoot deer during a limited open hunting season. And I'll tell you what, being a Cuyahoga County resident, we've seen deer populations we never saw. Okay, as more land is developed, all of a sudden there's less places for them to live, and so this is an issue that comes up. Is what should we allow hunters to go shoot the deer, and if so, how long, and that kind of a thing. It's a worthwhile problem to look at, I think. But I think that you guys probably can read through this and try the problems yourself. Whereas example 7 on page 352, this is on minimizing inventory costs. I feel like this one is complicated enough that I want to start with this, okay? Because if nothing else today, if I can get you to the point where you understand what's going on here, I think we're a lot happier, okay? So I was looking at the problems that, kind of go here. And there's a few different ones we could try. I like 62 maybe as an example, so maybe we'll do 62. Lingers luxury office furniture. Expects to sell 200 presidential desks a year. Each desk costs the store $600. There's a fixed charge of $600 per order. If it costs $300 to store a presidential desk for a year, how large should each order be? And how often should the orders be placed to minimize the inventory costs? What the heck do they mean by inventory costs? Well, and it's funny, I remember the first time I saw a problem like this, it wasn't office furniture, it was orange juice. And the example they used was at your grocery store, frozen concentrate you could buy. I mean, you could buy fresh orange juice, right? When I was young, you couldn't even do that. They wouldn't ship it up from Florida. They'd say no. What they did is they froze it into cans and shipped the concentrate up. You get home and you mix it with some water, and now you got orange juice again. Why'd they do that? Oh, not as good. Lauren says, no, I'm paying for the real deal.
Costs.
Costs? What kind of costs?
Distribution.
Yeah, I mean, you want to You got to keep it cold and fresh, right? Got to have a refrigerated car.
Big overrun.
And you just can't bring as much, right? If you can put it in these little cans, right, then you can bring more. Yeah. But whether it's the grocery business or the car business or in this case the furniture business, there are costs. And this is the model that we're going to use. Total cost, my inventory costs, are going to be storage costs plus reorder costs. And I'm going to follow that model here. Okay? So let me go ahead and work through this example with you and try and talk about what's going on. So, this is problem 62 as an example. Remember the question I want you to ask. When you get a problem, ask yourself, what are we trying to optimize here? I'll put the problem back up, and I'll read carefully, not the whole thing yet, but just jump right to that question mark. It says two things. How large should each order be, and how often should orders be placed to minimize the inventory costs? There it is, right? We want to minimize the inventory costs. Now, how do we do that? Well, this is what that little formula I said gave you, is that the total cost is a sum of two kinds of things here. We have storage costs plus we have reorder costs. I mean, here's the thing. If you're a furniture store, and if you know, well, we're going to sell 200 presidential desks, why wouldn't you just order 200 presidential desks? Well, think about it, right? Where would you put them? And I've seen, these small stores for furniture. I remember going to buy, and I've seen these little, when a small company tries to do it, they'll have stuff shoved in the back. These desks are on top of each other, but they put them away because if you had 200 of these things in a room, you wouldn't have room for anything else in your entire store, So this is where you have to do a little research about, well, when do we sell these desks? And how many should I have in my inventory, right? Because they take up space, and then I can't do other things. Now, there's another extreme. You could just say, hey, I'll order a desk every time that I need one. Then I only need one on display. But customers don't like that either. They would much rather be able to go home with a desk than be told they have to wait 2 weeks, right? So do you keep two? Maybe you keep two, then you always have one, right? And then if someone takes one, then you order another one. What's the issue there?
Making tons of orders.
Yeah. Reorder costs, right? Would you rather bring them all in one large truck? That'll keep this down, but that'll make that go up. Or you can keep your storage costs down by placing lots of orders, but that puts that up. So this is where there is an optimum. You guys see that? This is where it's worthwhile to analyze and do a little calculus. I like this problem. I think it's pretty cool. So if we're going to do this, I guess we have to really look at what are these storage costs and what are the reorder costs, okay? Now, look at what they ask. How large should each order be? And how often should the orders be placed? All right. And this is where, again, if I wanted to, I could do a table, right? I could say, hey, let's order 100, right? And then how many orders would you need for the year? Just 2, right? Every 6 months you make an order. The nice thing about doing that is that'll really keep down the reorder costs. You only order twice. But it would make this kind of big, right? And so there's a really valuable picture in the book that I could draw, but I may as well just show you. It's right here. This picture says an awful lot. They say, well, let's let X be the number of desks we're going to order, right? And now we're making an assumption here, right? We're assuming that once you order, you'll start selling some of those desks, right? And when you get down to 0, that would be the ideal time to have a new order come in, right? So this is, of course, idealized here. The other thing is that we're assuming that these things decrease linearly, right? But you have to in mathematics, when you want to do applied mathematics, you have to make some assumptions in order to be able to work with it. Okay. So we want to talk about storage costs, and we want to talk about reorder costs. I think reorder costs are easier. Okay? The reorder costs, well, pretty simple. Just figure out what's the cost per order times what? Yeah, the number of orders that you do. So if like I said, if we were just going to make 2 orders, it would be 2 times whatever the cost per order is. So that's nice. What about storage costs? Well, this is, again, maybe there's a cost per item, right? So you could say it's the storage cost per item. Do they give me that? Don't they give me that in this problem? Let me look there again. It says, there it is. It costs $300 to store a presidential desk for a year. That's kind of the annual cost. Now the thing is, are you going to have to store these desks for an entire year? Well, I don't know. What if you just made one order of 200, like I said before? How much would you have to pay to store these desks? What would be the storage cost if I just had one order of 200 desks? I claim it would not be 200 times 300. Why?
You would eventually sell them, so you wouldn't have them for a full year.
You wouldn't have them for a full year. Well, you'd probably have one of them for a full year, or 2 of them, or right? But there'd be some you'd sell right away also. You'd almost have no storage costs on those. So if we assume that, and again, this is not true. I understand that at Christmas people spend more, or other, that's why we have sales, right? To generate revenue. But if we assume that it's evenly spaced, then the picture, again, that I'm showing you here just about does it. If we just have one order, you start off with 200 desks, you end up with 0 desks. So on the average, you have 100 desks. And you take that average and multiply that by the 300 per year that you need. So, if it were me, and I said, it costs $300 to store a presidential desk for a year, well then, if I only made one order, my storage costs would be $300 times 100, not 200. Does that make sense to people? But like I said, if you want to cut down the storage costs, what you do is instead, let's order less. What if you only order 10 desks at a time? If you only order 10 desks at a time, then on the average, there's only 5 in the store all year long. 5 times 300, $1,500. That's not nearly as much as what I described before. But of course, if you only order 5 at a time, well, it just went up. Reorder costs. So again, it's the storage cost per item times, and this is the key, the average number of items. And so what I'm going to do here is I'm going to let X equal the number of desks in an order. And then I'll create a function here. C of X is going to be my cost function. Maybe I'll call it IC of X for inventory cost. That's what the book does. I like that. So IC of X is going to be something times, well, what's the average number of items? Well, if you order X of them, again, what that picture shows you is that on the average you have X over 2 at any particular time, right? So we'll call it X over 2 times, now what's the storage cost? Do they give me that? I think they do. Wasn't that 300? Yeah, it costs $300 to store a presidential desk for a year. So we're going to multiply 300 times X over 2 plus, and now it says each desk. So now what we have to do here is get the cost per order times the number of orders, so we can get the reorder cost. Maybe I'll start with this. How many orders are we going to make? Do you guys know what that's going to be? Well, that's worth talking about. So why don't we pause and let you think about that for a minute. And then if we have time, we'll move on to the cost per order next.
I'm still.
Because we're ordering to, like, just because of the problem, it says you're ordering, so in a year, it expects to sell 200 desks.
Okay.
That's a key fact, right? That 200.
Yeah.
Okay, so that's the math.
That's where I got the 200.
I'm thinking 300.
Because
I-
of this one.
Remember what I said in the last problem we did? Before break, I said, guys, here's the hardest part. When we were making a table, and we had numbers, and then we changed to try and write a function with x's in it, right? This is the same thing. I think this is the hard part. But I'm telling you that the numbers, making the table helped us write the function. And I did something deliberately when I was doing the examples. I said, okay, suppose we just made 2 orders, right? If you just made 2 orders, what would happen? There'd be 100 desks in each order. That would be x is equal to 100. Well, let me go back. If x equals 100, how do you figure out how many orders you just made? You divide. 200 divided by the 100, that'd be 2 orders. It really is dividing, right? Suppose you, well, and this is where Lauren said that the number of orders, whatever it is, you're going to take 200 and divide by the number in each order. Like if you had 20 desks, actually this might be a good answer. I don't know. I haven't worked it out yet. But if you said we're going to order 20 desks each time, no, that's not right. If you're going to have, if X is 20, if there's 20 desks in an order, how many orders do you have to make? 10. Right? So this is the idea. Last thing is cost per order. Cost per order. I have to do that. Now, for cost per order, I think if I pause and let you just look at what they gave you in the problem, I think you'll be able to get it. So I'll do that. I'll put that up here. I'll pause for just a second, and I think you'll get it because you've practiced this kind of thing already a few times. So we're coming up with this. I'm hearing it from both groups, but I'm also hearing some discussion. So I heard 600x plus 600.
That's what I was thinking, but that doesn't, because 600, it doesn't matter how many you get though. Like, so then the number of desks you get each time could be different.
I don't think you have to factor in how many desks you
Well,
X is the number of desks.
well, so what are we paying for here, right? We're paying $600 per desk, and that's why we wrote 600x plus $600. Yeah, that's the fixed charge. So really, you know what's going to cost us here? The number of orders, right? So if you have a lot of orders, you're going to be paying that extra $600 a lot. If you just made 1 order, what would it cost? Well, 600 times 200 plus another $600. But if you make lots of orders, then this fixed charge per order is what's going to cost you. You guys with me? Lauren has a question.
I guess I'm just trying to figure out what would balance it out.
Oh, right. You want to know the answer.
Yeah.
So do I. I want to know the answer too. But we really ought to work it out at this point rather than guess because it's sitting right here, right? Let's write out IC of x equals. So 300 over 2 is 150. So this is just 150x plus. And now here, I'll take that red and I'll distribute, right? And so I get, well, 6 times 2 is 12 with 4 zeros after it. And the x's cancel, right? This red x and that blue x cancel. So it's just, well, $120,000. That's the actual costs for ordering the desks. Plus, well, I need 600 times 200 over x, right? Because that's the, so that's going to be 120,000 over x. Well, actually, instead of writing over x, are you guys okay if I write x to the negative first power? Does that make sense? Because why did I want to do that? Because what am I about to do? I'm going to take a derivative, sure. So let's write IC prime of x. What would the derivative be? Well, I guess it would be 150 plus 0, which I'm not going to write. And then here, using bing bing, minus 120,000 x to the negative second. There's IC prime of x. Cool. And so what am I going to do with this? Well, set it equal to what? Set it equal to 0. So let me go to the next page because I'm really out of room here. I have 150 minus, was it 120,000? Over x squared equals 0. Is that what we had, guys? I had to go to the next page. Yeah? Okay. So I get 150 is equal to 120,000 over x squared. So I could multiply both sides by x squared, and I get 150x squared is 120,000. And so now I'll divide by 150. And I get x squared equals, and I think that works out really nicely, actually. Let me see. We need 150,000 divided by 120. Oh no, backwards, thank you. 120,000 divided by 150. 800. That's x squared, right? So if I want x, I need the square root of that. So I'll hit second square root, and then I'll hit second answer. Of course, 800 is not a perfect square, is it? So I got 28.28. So now what do? Well, how many desks should I have in each order, according to my calculation? 28-ish, right? So you're going to make an order for about 28 desks each time, right? That's what that's telling you. Order around 28 desks each time. Of course, then what I want to do, right? But then, all together we're supposed to order 200 desks. It won't come out. It won't come out evenly, will it? So you could tweak it, right? Yeah. So if I did 28 desks, and how many orders would you make?
7 orders.
7 orders of 28 desks?
Well,
So yeah, what's 28 times 7? That's 196.
yes.
And then, plus 4 extras that you could put in whatever you want. But, make orders of 28 7 times throughout the year. And then 29. That's going to give you a pretty good answer. Okay. Yeah, I'm going to talk a little bit, I think. Otherwise, I'm just watching you guys, and you could be doing this at home. So, number 58, right? Maximum sustainable harvest. And so, if you guys are looking at the books example, they're talking about this. They say, hey guys, we have this f of x, right? X here in this problem is the original elk population. In hundreds. Hundreds of elk. And then f of x is what they call the yearly growth curve. And now what you need to know is that h of x, and this stands for the harvest. It's kind of funny to be thinking of harvest for elk, but hey, hunting season, that's what people want, right? venison, right? Take your original elk, okay? Subtract off the yearly growth, right? The idea is this: we want to maintain a certain population. We don't want less deer at the end of this year than we started with. We don't want more deer at the end of the year than we started with. We want it to level off. So we really would like to know, how do I get the most harvest when I do this x minus this f of x? Now in our example, for 58, they give me the f of x value, right? 1.75x minus the 0.003x squared. So I can compute h of x. 1.75x goes there. And then minus 0.003x squared. Okay? And now I think you guys are probably in good shape. You have that in parentheses. Go ahead and see if you can optimize h of x, the harvest, and then we ought to be able to answer the questions. Right? If you think about your harvest, yeah, I'm going to rewrite it the other way. It doesn't matter, but if we write it as f of x minus x instead of x minus f of x, that makes more sense, right? Because you're having growth in your population minus what you started with. So if you add, because I'm going to end up with a negative answer, and I don't want that. How much can we harvest? Well, we can harvest however much grew from the original population. So let's do it the other way. All right, so what was it? It was 1.75x minus 0.003x squared minus x. And so my h of x is just going to be, well, 1.75 minus 1, so I have 0.75x minus 0.003x squared. There's the harvest. So, let's compute the derivative. 0.75 minus 0.006x. Set the derivative equal to 0. 0.75 is equal to 0.006x. I'll divide to get the critical value. So let's work that out. What does x equal? 0.75 divided by 0.006. Ha! 125. What a beautiful number that is. Okay. So what does that mean? It means that to optimize things, we want the original elk population to be 12500. Right? So ideally, the original elk population should be 12,500. So that's one thing. And this actually asked two questions, right? They said, determine the optimal population size and the maximum yearly kill that the population will sustain. So that means we want to write down what h of x is, right? So this will give us a maximum kill of, well, how do you compute that?
Put 125 into the original function.
Which function?
The 0.75x minus,
Yeah, h of x, right? So we'll do h of 125, and then we'll have it. Okay. So I can take out my calculator again, and I ought to be able to get it. So let's see, it's 0.75 times 125 minus 0.003 times 125 squared. And that's 46.875. And again, the units are also going to be in hundreds, right? So we have 46.875. And so the maximum kill would be 4,687.5. I don't know how you kill half of a deer. So maybe we say that and round up. All right, guys?